Good afternoon, everyone. Test, test. Okay now? Okay, good afternoon, everyone. Welcome to Technical Session 1. My name is Shane Hermoso from APNIC, and I will be the moderator for this session. I'm also the co-chair of the APNIC 60 Program Committee, so I'd like to take this opportunity to thank all of the PC members who have volunteered their time over the last few months in coming up with the program for the technical sessions that you will see today and tomorrow. Uh, with that said, let's start. we will be we will be having 3 speakers, all excellent and very engaging, and they will share information around a common topic on networking protocols. Let's kick it off with the first one. The first presentation is on GIS for infrastructure. Sorry, let me find it. For infrastructure resilience, please welcome John Brewer.
Shane, is this your coffee? Hello, my name is John Brewer, and I'm not going to talk about networking protocols at all. This talk is about using geographic information systems for digital infrastructure resilience. I am based in New Zealand. I have some background in IP networking going back 30 years now. I have some background in radio access networks, and to these days I do some internet governance activities with APNIC, with APNOG, and I do a lot of consultancy to a lot of different organizations. So this talk is about some work that I did for one of our regions in New Zealand. And this work was commissioned after they suffered from a cyclone. So I've been making maps of digital infrastructure for 20 years now. And a couple examples of that. On the left-hand side is a map I made, I would say, 19 years ago, of the coverage of a wholesale radio access network that I built in New Zealand. So the red lines being microwave links, the green areas being radio access coverage, and of course the blue being water, because New Zealand is an island. Now, that was done in a very expensive tool, a radio propagation tool that we paid tens of thousands of dollars for. But up on the upper right-hand side, I've got Google Maps, which I did just around the same time. And these were sales targets. So I spun up this map using no coding at all. And I was able to encode information into a spreadsheet and just display it on a map and give this to my sales and marketing people and let them go after sales targets and look at it on a map. So that was really cool. Down in the lower right-hand corner was another free tool called Google Fusion Tables. And Google Fusion Tables was kind of an evolution of maps and allowed you to start putting polygons that we can see here. And in this case, we've got polygons of DSL and VDSL coverage of one of the regions of New Zealand called Taranaki. So the kinds of infrastructure maps that I've made, radio coverage maps and sales targets maps, maps of schools that are near fiber, maps of unconnected communities for a few government agencies in New Zealand, universal service planning maps. We in New Zealand look to have universal service for broadband, which means we want everyone to be able to get access to a minimum standard of broadband. And to do that, we need to know where people live and what coverage they have everywhere. Broadband affordability maps. What we don't have in New Zealand is universal access, so we don't care how much broadband costs. We just care if you have it or not. But it is important to understand the wealth of your community and whether or not they can afford your solutions, and this is something you do through maps. Submarine cable maps are things that I've done for a few presentations at this conference, at Apricot and some other regional conferences, and subway maps. Next slide here. That is a subway map of submarine cables. On the left is a submarine cable map that I would have presented at the APNIC meeting we had in New Caledonia. I don't know, is Bertrand here? Yeah, what year was that? 2018. Okay, yeah. 2018. So that map on the left was the state of cables in the Pacific Ocean in 2018, and that map on the right was kind of a subway map diagram of it, because it's kind of important to know not just where physically they are, but how logically the cables connect together. This is a radio spectrum interference map. A map of space lasers. This is a map that shows connections between fixed geosynchronous orbit satellites and ground stations in New Zealand. So these are the actual positions. Now, there's a lot of free data that you can use in mapping, and in New Zealand, as in Australia and a lot of other countries in the world, we have our Geological and Nuclear Sciences organization offers free data. Our Land Information Organization offers free data. Our radio frequencies, this is the equivalent of the FCC or Ofcom in the UK. They offer data on where radio frequencies are in use. Our Institute of Water and Atmosphere offers a lot of free data. And our statistics department, of course, offers a lot of data that's tied to addresses or locations. But outside of New Zealand, if you're making maps like these for infrastructure, you can get good data from the ITU, including on submarine cables. You can get data on the terrain of the entire Earth from the NASA Shuttle Ray Topography, or SRTM, Shuttle Radar Topography Mission. That's how you get SRTM. You can get information on solar radiation. Very important if you're planning solar power for your infrastructure. And you can get good information from the World Bank too. Once you get this information, it can take quite a lot of work to get it into a format that is usable. And for one of the projects I did on affordability 10 years ago or so, I tied up an instance of AWS that had, I think, 36 processors or something, and many gigs of RAM, and I tied that up for a week, just doing point and polygon queries to try and find where particular data was located. So, where does resilience come in? Well, resilience is interesting. Nobody wants to pay for resilience of their telecoms infrastructure. They just want cheap. There's no real business case for resilience in telecommunications until you find that there is a business case for resilience. So Cyclone Gabrielle in 2023 affected a few regions of New Zealand with high rains and flooding, and the biggest problem that we had was the loss of power. And as a result of the loss of power, we lost access to a huge amount of infrastructure. So this project was kicked off after the sun was shining again. A few months later, after this incident, the regional government said, we need to find out what to do to make sure we don't lose our telecommunications again when we have another big storm. And this is why. The reason the government was so eager to not have a repeat of this incident was that as soon as the storm hit, some communities lost 80% or more of their cellular communications. And these are quite remote communities, and communities in which people don't use landlines anymore. So entirely disconnected towns and villages and rural communities for days and days and days. There were some communities that were offline for a week, unless they had satellites. That was it. So this isn't just planning for a rainy day. The map of infrastructure assets was a way for the regional government to see which carriers had infrastructure in their region. So they wanted to know who had cell sites, who had fiber cables, who had generators, who had all of the layer 0 assets that make up our telecommunications networks. And then they wanted a paper to say, well, how could natural hazards affect these systems in the future? And really the only way to do this is by starting with a map. So what kind of infrastructure? Fiber, cables, cellular backbones, fiber backbones, microwave trunk routes. In terms of power, it's important to know where your substations are, where your lines are, where your transformers are. It is important to know about the national grid, because the national grid connects to the region in 3 places in this particular region. It's important to know about where the national grid's spans are, where the big overhead power lines are, because in the case of this cyclone, one of the major interconnection points was flooded, and so the region lost power completely. And also for the community, it's important to know, well, where are the hospitals, where are the emergency services transmitters, where are the command centers where the emergency service organizations come together to respond to a disaster. And this is easy. You know, you saw in my previous maps, well, it's been possible to put pins on maps for 20 years. It's been possible to draw lines on them to say, well, here are all, in this case, we've got colored microwave links, which are the straight lines. We've got blue lines in there, which are fiber cables. We've got dots on this map, which are cell towers or, I guess, cell towers or DSL cabinets in this location, or even end users. So this is easy. Infrastructure mapping is relatively easy, it's relatively straightforward, and the tools are free. You can use entirely free tools to do all of the work that I've done, and I mostly did use free tools for the work. So, infrastructure mapping is easy and useful. What about the hazards? So things that we have to consider in New Zealand, number 1 is landslides. And that's because we've taken a country which used to be covered in trees, and we've cut most of the trees down. And we've replaced those with sheep. Lots and lots of sheep. More sheep than people. Some cows too. So as a result of putting cows and sheep on grass where there used to be trees, when we get too much rain, the land slides. And when the land slides, if you have a utility pole on it, the utility pole goes down. If you have cables buried in the land, the cables break. You don't want to have critical infrastructure separated from your users by a landslide. Tsunami inundation. Now, we have not had any significant tsunamis in New Zealand, but as we all know from Fukushima, tsunamis are a major threat. And so we know through modeling, in this case modeling that has come from our government agencies, which parts of the country are most at threat from tsunamis. And we know it's probably not a good idea to build a cable landing station in a tsunami zone. It's not good to build an electrical substation in a tsunami inundation zone. People have done it anyway before they knew about this data. So now that we know, some things should probably be relocated. Detention dams. So this is where you've taken a stream and you've put a dam up there in order to hold water, maybe because it's the water supply for your region, or maybe because you're irrigating with it, you're growing crops with this water. When you have an earthquake, when you have too much rain, the dam can break. Anything below this dam could be washed away. This has happened in New Zealand and does happen all over the world. Flood risk areas, of course. These maps, people in our country thought these maps were silly. They thought, oh, there's no flood risk here. It hasn't ever flooded here. And then we have a cyclone like Gabrielle, and we look at the photos from space And they look just like these flood risk area maps that were made by a computer. It is true, just the height of the ground and the slope of the ground means that water is going to accumulate in some places. Liquefaction is when you have an earthquake and the soil under the ground turns to mud when you have an earthquake. So as a result of the shaking, it turns to mud. Now, when you have a liquefaction zone, if you have a utility pole, if you have a building, it's gone. It won't exist after the earthquake, and we know this from earthquakes in New Zealand. We had a significant one in Christchurch in 2011, and as a result, the city of Christchurch, there are probably 20% of the city that existed in 2010 is now just parkland with nothing built on it, because that land doesn't support infrastructure, doesn't support houses, doesn't support buildings. You don't want to build on it, because when the earthquake happens, everything shakes like it's on jello. Speaking of earthquakes, active faults. So we know where the fault lines run in New Zealand, and we have good maps. And these maps are used by our city councils to allow or disallow building of houses and building of buildings. They've never really talked to the telcos about this, though. So telcos have built new fiber optic cables that have gone directly over fault avoidance zones, which means that when we have earthquakes, we have fiber breaks. And so there's a real disconnect between the planners of telecoms infrastructure and the regional planners who know where the earthquakes are. We do have volcanoes in New Zealand. We haven't had a significant eruption on the mainland in a long time, but we have had in the past. And when you have a volcanic eruption, you get ash. And you think, oh, who cares about ash? But if you have a data center, your data center has air conditioning. It has fans. All of these fans will fill up with ash and stop working. All of your air filters will be clogged instantly. You need to get out there and clean them. These maps can tell you where is the ash going to fall and how dense is the ash going to be. In addition to clogging up the filters, volcanic ash combined with rain can cause electrical faults. So you can have arcing across power lines because the ash and the rain together creates a conduit, a pathway for the electricity. Really all sorts of interesting things to consider with volcanoes. And shake maps. So in addition to knowing where the fault lines are and knowing where the liquefaction zones are, we actually know through modeling which parts of Earth are going to shake more or less during an earthquake. So when I planned a radio system for New Zealand's Parliament, I did this planning in 2009 and 2010 for a radio system that backs up the Parliament in the case of a disaster like this that is still in use. I had to consider where the other side of the radio links were going to be, and I had to use shake maps. I had to find hilltops with very low shake and hilltops in different fault zone areas so that New Zealand. This map is from California. This is the one data source that we don't really have well sorted in New Zealand because we don't have significant forest fires. But California, on the other hand, has forest fires every year. And they know what are the risk areas. And their utilities regulator, the California Department of Public, DPUC, someone else from California might know, their regulator has required telecoms operators, when they build cell towers in high fire risk areas, they've required them traversed high landslide risk areas, and there were landslides. So as a result of this cyclone, the road was out and the power was out. And there was no way to deliver fuel to the backup generators, and the batteries ran out after a few hours, and it was just a bad situation. And when you have a storm like this, it's not safe to fly a helicopter because you're still in the middle of a storm. So having critical infrastructure in an area that's inaccessible in a storm doesn't work. Something that you need to fix before the next storm. In this case, I've blotted out the names of the roads and the river here, but we had all of the fiber cables from all 3 of the telcos and one other infrastructure provider. So I think we had in total 5 different fiber operators with cables out of the region across the same bridge. And the bridge was washed out. By washed out, I mean trees came out of the valley into the river and destroyed the bridge completely. And when they destroyed the bridge, of course, all of the fiber cables were cut. Now, they got this up quite quickly and quite creatively, I think maybe the next day because it was so important, by using a drone to take a piece of rope across the river and then using that rope to bring some fiber cables across and propping them up and splicing them back together. But the better way would have been to not have all 5 of these providers crossing the river in the same place. And in this case, fortunately, this incident was a cyclone, but when we do have an earthquake, we have another example where the diversity of the fiber cables is that they're buried on different sides of the road. So here again, we have all of the telcos in one place, all of their fiber cables on the southbound path out of the region, crossing the same well-defined fault avoidance zone. The local authority will not let you build a building in this place. You can't build a shed, you can't build a garage, you can't build anything there, but the telcos didn't ask, and they don't seem to have the ability to regulate the telcos, so the telcos have just dug up the road and put their fiber cables in. But when we have an earthquake here, all of those fiber cables will break at once. And the way to avoid this problem is to make sure that at least one of these fiber cables is taking a different route through an area that is not going to separate by a few meters the next time we have an earthquake. And that's it. That's me.
Thank you, John. We have time for maybe a couple of questions. If you do have a question, please approach the microphone and introduce yourself and your affiliation.
Oh, thank you, Jeff.
I was being lazy and sitting down. Look, do you know in economics the example of the ice cream sellers at the beach?
In economics, the example of the
Ice cream sellers at a beach.
ice cream sellers at the beach, no.
The optimal behaviour is they all crowd beside each other. They will not disperse because they all want the optimal position, and each of them make an independent decision to go to the same spot. You are pointing out that in a large, diverse market of providers laying infrastructure cables, that they all tend to optimise their own money, and they all pick the same route. And each of them is making a thoroughly rational, personal decision about where to pop their infrastructure, but the common result is an unacceptable level of vulnerability. How do you stop them acting in their own self-interest?
In a local market, the answer is regulation. Now, in a global market, the answer is commerce and contracts. Now, I have been a very busy man in the past few months. It was my intention to make one more slide for this presentation, and this one more slide was going to show Google's new submarine cables in the Pacific Ocean. Up until 5 years ago, all submarine cables in the Pacific took one of two routes, from the Pacific Northwest in the US in a big arc, kind of going up around Alaska and Russia and Japan, and then coming down into Japan, or going the long way from California to Hawaii, from Hawaii to Guam, and from Guam to Southeast Asia. So this was it. These were all of the cables except for one called Southern Cross, which kind of came down to New Zealand and Australia from California, again stopping via Hawaii. Google, in the very recent past, has decided that these are very vulnerable routes, and they're either vulnerable routes because of the potential for earthquakes or tsunamis or volcanoes, as we had in Tonga, leading to underwater landslides. They've also recognized that there are some geopolitical risks, and there are some places where cables are interfered with mysteriously more than other. And so Google has decided to build a mesh of cables across the Pacific. And they have started building a cable from South America to French Polynesia, from Valparaiso in Chile to Papeete in French Polynesia, and then from French Polynesia to Suva in Fiji, and then from Suva up into the North Pacific. Previously, we didn't have any bridge between the center and South Pacific and the North Pacific. So we had these cables that touched the North Pacific via Guam, and we had the rest of these cables that went through the South Pacific, Southern Cross, and so on, centered around Fiji. Google has made some cables that are bridging these areas. They're also going from South America into the Pacific. And they've also decided on a new set of routes to get to Singapore. So to get to Singapore from the Central Pacific, it used to be that you came up through the Strait of Taiwan and over to Hong Kong, and then down, around the South China Sea, through this zone of 7 lines or 9 lines. I forgot about exactly what this zone is called. And now, Google and Facebook and a few other organizations have decided to build cables that take a southern route from Guam, going south through the Philippines around Davao, and south through Indonesia, between Indonesia and Australia, to get over to Singapore. And so here we have the threat avoidance of both geological threats and political threats. And this has come probably because of pressure from their customers. I can't think of any reason they would build these routes in a more expensive way unless they really had some commercial pressure to do so. So they're not all crowding around the same spot on the beach with their ice cream, because their customers are saying, we'd rather buy our ice cream over here where it's quieter. I saw another question somewhere. Anyone else? Have I taken enough time, Shane? Awesome.
Thank you so much, John.
Thank you. All right.
So our next presentation really is about networking protocol. So here to present about QUIC is APNIC's Chief Scientist, Jeff Houston.
Hi, Jeff Houston, APNIC. The geopolitics of submarine cables is absolutely fascinating, John, and we could talk all afternoon about this. The latest move, and I think it's some years old now, from the American government, is that any submarine cable that surfaces on American territory, they have a say to refuse where that cable might also surface. So if it touches any part of what the US regard as US territory, then Hong Kong's got a problem in landing a branch of that same cable. And so part of the reason why you head over to South America is that, as far as I'm aware, at least this week, the US don't own it. Things could change. But let's move on. I want to lift this up into the area of transport protocols. I don't think any of you are old enough. Who was around when telephones existed? Oh, thanks, a couple. And you might recall that the way we did engineering of transport was that the handsets are dumb. Just a speaker and a microphone. All the intelligence of trying to get that application speaking through the network was a network property. And so if you wanted to preserve the timing of voice, you actually needed the network to switch voice. You can't do that easily with a packet switch network that doesn't have enough resources. So you either give it a lot of resources, we couldn't afford that at the time, or you pushed a whole bunch of cruft into the network called virtual circuits, time division switches and so on, to sort of support inelastic transport. Now, oddly enough, that's turned into a feature in today's world. SRv6, MPLS, RSVPTE, you know, the usual dictionary of crap that vendors wheel out to try and sell you solutions that are based around a 1970s view of a networking world that has disappeared decades ago. That's all it is. Because by putting computers at either end, by allowing us to actually transform the application, the signal, and match it to the network, we can do a whole lot more for a whole lot less cost. And the true brilliance of IP, the one spark that you'd say, Vint, Bob, you did it right, is not connectionless networking, not datagrams, nothing about that. The true genius was actually the protocol TCP, that transmission control protocol, because that transformed everything. That allowed us to take really poor networks that lost packets, had very variable response, all kinds of things happened, and produce a coherent end-to-end signal. You use it for data, and you use it all the time. The network in this room is crap. We all know this. If anyone's still there online trying to get packets through, good on you, but it's not easy. But somehow, you're still getting stuff through. And the reason why is actually TCP. So TCP was the original, if you will, spark of invention of the internet. And what it did was take stuff out of the network. Stop trying to cram more code into your routers and so on. That's irrelevant. It's kind of a stupid way of doing things. Push it out to the edges, and at the edges look after it. But that was close to 50 odd years ago. And you kind of go, well, nothing's changed, right? Wrong. Slowly and surely, things are changing, because TCP certainly was the workhorse of the internet. And if you think about it, what it does is fantastic. You know, it takes a network where every packet's an adventure, stuff gets lost, stuff gets reordered, stuff spews around, and instead allows you to recreate that stream of bytes that you pushed in as the same stream of bytes you get back out. How fast does it go? As fast as the network will let it. It will go as fast as you have networking. Not quite up to terabits, but very close. You know, there is no maximal speed. It will just simply take what's available and use it if it can. It's a brilliant piece of engineering. And it's the one reason why you're all here today. The only reason why. Because by pushing it out to the edge, we savagely stripped cost. We took the telephone companies and unseated them and actually created an entirely new industry, which is the industry you work in today. So TCP did a huge amount of stuff. But oddly enough, it's not that good. It really isn't. Let's say I'm using Apple's iOS and I'm writing an application. I'd really like some changes to TCP. I'm just me. Apple are bigger than me. What's my chances of getting Apple to change? 0. What about if I'm Google running Chrome on iOS and I want TCP to change on this phone? What are the chances of doing that? 0. You see, somehow that implementation of the transport protocol is not necessarily independent of the underlying operating system kernel. It's tightly bound in, if you might remember your days of working with Unix. And that's a problem if someone else controls that kernel and you're just a guest application. Maybe that's not what you wanted. These days, we get a lot of work out of parallelism. You don't just go, well, here's a web page with 60 different components. You don't go fetch the first, fetch the second. God, no, we don't live that long. You send it out all at once. You bring in everything. Parallelism is brilliant. But these days, you need to set up a TCP stream for every single one because it doesn't really support multi-stream very effectively. Head-of-line blocking kills it. We tried multipath. We ran away screaming. It's just too hard. It doesn't work very well through NATs. And in fact, we had to change the way NATs work to actually know that it was supporting TCP to make sure the NATs didn't muck around with the addresses on a live TCP session. So TCP isn't address agile. And then folk discovered that all I've got to do, if I'm in the middle, to make you go slower, is to reduce your advertised window size. And there are all kinds of network-based middleware that tried to modify the way things work. I'm an access network. I happen to not like Netflix. God knows why. I'll just make Netflix's packets flows go slower, because I can. Because those control protocols in TCP are actually open to the operators of networks on the wire. TLS is too slow. TLS is brilliant. Encryption's fantastic. But it's a second step. It's another round trip time. And if you're trying to shave every last millisecond you have, doing TLS after you've set up TCP is kind of, why? Why did you wait? So TCP isn't everything for everyone. It's good, it's really good, it's what you all run, but we can do more. Now, there's been a lot of folk and a lot of PhDs written over the years about trying to fix TCP as TCP. Still using the same TCP protocol number, what is it, 6? You can muck around with things. You can change the handshake parameters. You can change selective acknowledgement. You can do a certain amount of changing in TCP, but at some point, you stray too far and the other end doesn't get you anymore. You kind of walked away and it's no longer TCP. And part of the issue is not that the other end really cares, but it's all that middleware. If you're running through a NAT, you can only do a certain number of behaviors in TCP before the NAT goes, that's not part of the same session, I'm going to drop your packet. Or load balancers, or all the other kinds of middleware that you stuff into your network. They tend to actually reduce the flexibility of trying to change TCP. You can't. Okay, let's forget it. Let's just go to an entirely new protocol. There are 105 new protocol number slots in the IANA registry. Pick one. Occupy the space. Define one. We tried this with V6, and look how long it's taken just to do that, and that wasn't even a big change. If you really wanted to change things, a new protocol is doomed. Everything needs to change to recognize the new protocol. That's not going to work, okay? So at the internet the size we have today, you're kind of fenced in. It's sort of TCP, and it's just TCP. It's not even V6 these days, and it might take us decades to get, even further with that. So what can we do? If we really want to change TCP, what can we do? I would actually argue that the lessons from the past are amazingly, amazingly relevant. When you use the word internet, do you know what it means? It actually was built as an overlay network. At the time when this was first being thought of, there were packet-switched X25 networks, there were baby bits of local area networking, there was all kinds of stuff out there. And what the researchers in the ARPA project around this wanted was an overlay that every time you hit a network, you kind of tunneled through it, but when you got out again, you recreated that overlay and kept the packet flowing. So the first hop could be X25, then you drop over to a FIDI ring. For those of you who were born after 1980, all of these terms are really foreign, but at the time, that was the language we spoke. Across to a FIDI ring, then onto an Ethernet, a bit of frame relay. The overlay, the end-to-end was IP. It was basically encapsulation. So why not do it again, the same technique? There are two protocols that are universally supported out there. One is TCP and the other one is UDP. So instead of trying to, if you will, invent a third protocol, why don't we just layer it inside UDP? Now the beauty of that is the difference between UDP and IP is so slight it's not funny. It's a really minimal encapsulation of the underlying protocol substrate, but all the middleware thinks, oh, you're running UDP. You're fine, I'll let you through. And so if you think of QUIC as TCP++, and you fool the network by running it over UDP, you're pretty close to what it is. So it's a mashup. And the essential thing is, it is TCP to some extent. It's put on top of a common UDP substrate, but it's also got TLS. And so we've combined, instead of TLS sitting above TCP, TCP handshake, TLS handshake, let's get busy, it's kind of, let's start doing TLS and TCP together in the same round trip time to do the handshake. And by the way, let's encrypt the lot. Every last little bit, even all the control bits, are encrypted inside QUIC. There is literally nothing to see beyond the fact you're running UDP port 443. The rest is a mystery to the outsider. So all of the rest, right, is sitting inside QUIC. So the responsibility for data integrity, session control, you know, the usual TCP congestion control and so on, is just sitting inside that package, right up near the application. Now, some operating system platforms provide an API for QUIC, but you don't have to. All the service you need is UDP. And you can take the entire implementation of QUIC and run it inside your application in user space. You don't have to rely on anybody. So if you don't like the way it works from someone else's, run your own. So it's the transport protocol that an application can run as an application. And that's some of the magic of why QUIC is so seductively kind of neat. It gives application folk a degree of freedom and independence from the underlying operating system that they've been wanting for decades. It kind of frees them from the tyranny of the OS. So, you know, the OS is no longer anywhere near as important. So what does QUIC do? We've learned a lot in 30 years, and it's so much more than encrypted TCP, so much more. So I want to do multiplexing, and I don't want head-of-line blocking. So inside the same encrypted session, encrypted sort of state, I can do multiple streams that have independent control over their flow. So one could block, the other one can just keep on going. There's no shared head-of-line blocking, no fate sharing. The combining of that handshake, I do a TLS and a TCP exchange at the same time in the same packets, means that I've shaved an entire round trip time out of session setup. You go, boring? I'm sorry. This industry sends billions of dollars to shave each millisecond over one, you know, shaving that initial connect time. We are obsessed with making the internet faster. And Quick certainly does that simply by eliminating unnecessary round trip times. Each of these streams can have independent flow control. So if you really want to put different flow control disciplines on each part of that multi-stream, up to you. And as I said, third-party interference, packet interceptors, all that kind of stuff, not there. It's all encrypted. All those control bits can't be mucked around with. So this is this kind of true implementation of the OSI 7-layer model that said, when you're at layer 3, layer 2 can't muck with you. When you're running Quick, the network can't muck with you. There is nothing to see. And that has actually been a real asset, because if you've been watching closely the wars in the mobile world about those greedy applications taking all the mobile spectrum bandwidth, according to the mobile service operators, and the application folks saying those disgusting mobile operators are trying to hold the gun at our head and force more money out of us to run our cute applications. Quick solves that in the application's favour. It's really hard to muck with an application running Quick because it's not exposing any control points that make any difference at all. And last but not least, for the computer scientists among you, we've finally got a remote procedure call model that actually works. You can actually do reliable datagrams, which TCP could never do because it couldn't, and UDP was never reliable. And so interestingly, you can do RPCs for real. So what goes wrong? NATs. Mentioned before, NATs have two modes of behaviour. There's the TCP mode of behaviour. It senses the initial SYN exchange, and it creates a binding that it will hold until it sees a FIN or a reset, or until hell freezes over, 30 seconds of inactivity or some other external event. But NATs are tuned to TCP behaviour. They won't drop the binding until they think the session has gone. But you're running UDP. Oops. How long should a NAT keep that session open when all it's seeing is stateless UDP packets? And the answer is, wow, not long. Even if there's activity, not long. And so what do you do? Well, Quick said, that's fine. That's perfectly okay. You can change the addresses of the other party I'm communicating with however you want. Fascinating. How do the other party know that it's still me, that I'm the one that's talking to you and not someone else? That's interesting. Quick uses the concept of a connection ID. And that's part of that initial setup, that the two ends inside the encryption envelope exchange this sort of magic ID that says, I don't care what the outer level IP addresses say, if it has this connection ID, it's really me, believe it. And so this means that whenever you get an address change, the other end says, that's got the same connection ID but a different address. Challenge, and I go, yep, still me, response, and it just continues on. So oddly enough, Quick is address agile to the point that it doesn't mind about NATs being in the path. NATs are fine for things like Quick, and it will not alter its functionality. Interesting. What's your maximum MTU on your network? If you make it too big, you run into all kinds of problems. If you make it too small, you run into all kinds of problems. Most of you just say, oh, it's 1500, I hope, and I hope I don't run into trouble. But fragmentation is terrible. Fragmentation from the security perspective is, the behaviour from hell. How do I know that this packet is genuine, not someone trying to intrude into my session? Because as soon as you lose that first packet, you have no idea what the trailing frags actually mean. Quick solved this by saying, you can't fragment. There is no such concept. It basically says 1200 octets. That's what we do. If you don't support 1200, you can't run Quick. If you do, you can, and that's it. Everything has to fit into that payload. Interestingly, it never retransmits lost packets either. Every retransmission gets a new packet number. No ambiguity at the network level. None whatsoever. SAC gets a whole lot more tolerant. 256 packet ranges, So you can lose an awful lot of packets and Quick will go, no problem, I can repair this at speed. And it separately encrypts every single packet. So it doesn't rely on the next or the previous packets. Each packet that Quick sends is its own encryption. And you can load multiple Quick packets into a single UDP frame if you feel adventurous. So it's got a whole lot of flexibility. And in fact, it's another level of multiplexing and structuring. So that when you see a Quick flow, inside that flow are a number of data streams which are themselves reliable data flows, or they're itself a datagram style remote procedure call or similar. And each of those streams have their remote congestion control, flow control, etc. So what's going on here is that the structuring of Quick is way more flexible. I've been told I have 5 minutes. Oh, that's right, and time for questions. There will be no questions. So I think it's the protocol for the 2025s. It's really what we've been waiting for so long, it's not funny. Things you can't do, you can't load balance. Why? There is no 5-tuple that's visible. Oops, you really have to think hard about how you want to load balance in Quick. And you've got to bring the load balancer into the encryption envelope to find that it's all part of the same session, because Quick isn't going to help you if you're just simply looking at the packet headers going, I know it's part of the same session. Those of you who've been relying on the Intel NIC cards to actually do all your session segmentation in TCP, oops, Intel have some work to do, or someone does, because TCP offloading is yet to be done in the firmware of the interface cards for Quick. It'll happen, but it might take a little bit of time. How much Quick is out there? Well, more than you'd think. For about 10 years or so, Google has been running Quick, and then Apple came along and did it again differently. So in what we see right now is that Apple, if this goes back, uses a DNS trigger. That if you say in the DNS, here is the address of a service, DNS, by the way, I serve Quick, then you'll see Quick being used instantly. And there's a hell of a lot of queries for this special DNS label that says, I'm HTTPS. What about in HTTP itself? The old way is, the first time you come, let's just talk TCP. But I'm going to add an alt service header into the HTML that says, the next time you come, let's talk Quick. And that's what Chrome uses. So what we see is that Chrome, 65% of the world uses Chrome, can do Quick, but only on the second try. And Apple, about 16% of the market share or so, roughly 15, does it straight away, first up, because if you put it in the DNS, it does Quick. How much Quick is out there? About 31% of the world's traffic, according to Cloudflare, is actually using Quick right now. If you really push it, as we do, and we push, you can get up to 70%. If you really try hard saying, come back again, I can really do Quick. Are you able to do Quick yet? We see about 70% of the world can use Quick. 70% of the world is basically everyone except China and Iran. Everyone else can use Quick. I don't know what the Chinese have with this, but you know, it's their problem, not mine. Payload sizes, most of them are around 1,200. A few are around 1,220, 1,240, but generally, yes, Quick packets are below 1,500. We've done a fair deal of work in this and found that basically Chrome uses HTML, Safari uses the DNS. Who uses Quick? YouTube, Facebook, Instagram, all of the video streamers. Why? Because I can do it better. I have control over the flow control. It's up in the application space. It encrypts everything. You can't muck with me. There's no visible server name indication in TLS exchanges. I'm not leaking any information at all. And that's, in today's world, some folk consider to be extremely important. What about TCP? It's declining. It's not as fast, it's not keeping up. There's a whole lot of resistance to network operators to try and interfere. The application level folk have lost patience with you. They're moving on. They're not waiting for you. Quick is now taking on from that. And so, quite frankly, a bit like V6, normally this transition would take a few decades. I've still got a couple of minutes. Normally this would take a few decades and still would only be halfway there. QUIC, I think, will be done inside a few years. Because quite frankly, it's not up to you or me or the network operator. It's up to the application folk. It's up to the browser folk and the streaming folk. And they have demonstrated far less patience and far more agility to get things done and just not worry about the rest of us. So this will happen extremely quickly. It'll all be over for TCP quickly. What does this mean for the internet? Wow. There's a big socio-economic change. It used to be that all the money was in networking. It was the telco world. This is why Cisco was rich. Routers cost a lot of money, applications were free, who gave us stuff, right? But all of a sudden, what's going on is that the networking role has declined in importance and in economic value. Laying cables is a bit like laying sewerage pipes. It's basically a commodity exercise that you cannot distinguish. And all the SRv6 on the planet won't help you. MPLS is not the answer. You're in a new world where the money has moved up into the application layer. And with it has come the transport protocol as well, because that's now an application function as well. So QUIC's view is that all the money is now where QUIC is, right up in the application space. And that's kind of the space that we're in now. What does this mean? There is no mutually supportive relationship between applications and hosts and network. Mutual distrust, suspicion, and outright hostility would be the best way to phrase it. Networks are losing that fight for regard and money. The application world has won completely. And what does this mean if you're a network operator? Wow. Not looking good, is it? I don't think there's any look coming back from this either. They've kind of lost that economic battle. And quite frankly, it's now a last mile commodity stuck between users and CDNs. There's very little space for networks to operate. What do you do when everything is encrypted? I don't know. Find another job, I guess. I really don't understand where you go from there. It has really come in for this. The operators have actually tried to extract too much money from networks, and the rest of the world has gone, nah, not going to play that game. So just remember those words from Peter Thiel, the guy behind PayPal, Elon Musk's best mate. What you can't dominate, you commoditize. You strip the value and force it down in value. And that's what's happened in this world. The carriage is no longer an inescapable monopoly. It doesn't make money. You'd be lucky if it doesn't lose money, and that's about the best you control. Control over the platform isn't control over the user. Operating system being pushed back, Windows doesn't matter, Android doesn't matter, iOS doesn't matter. It's not valuable. Everything is further up in the stack. And that's the world we live in, like it or not. Thank you.
Thank you so much,
no
Jeff.
time. There is no time,
You're
is
right
there?
on time, but there is no time for questions. So Jeff will be around. Please feel free to approach him whenever you have questions around QUIC. Thank you.
Thank you.
All right, our last presentation is about IPv6, the neglected younger sibling. Please welcome Maria Matejka, the BIRD team lead. Thank you.
Hello, I'm Maria. I'm an IPv6 maximalist, and more about me later. We have been sitting here for a while, and we had some, you know it, lunch, and so to like make it flow. How much is 1 + 1? Oh, thank you. Let's go harder. Well, yeah, it's 2, of course. Let's go harder. How much is this? I'm not going to read it. It's something, a little bit under 4,000. This was a little bit harder, wasn't it? Yeah, so let's try this. Who remembers this from school? And I still hope that most of you have seen it in school. So you at least you at least remember partially what's the centroid of a triangle, and you suddenly find out that yes, you remember this definition, and you even remember that it's splitting the three medians in ratio 1:2. And what about this? Who of you can at least think about how to solve this? You can show your hands if you want. Who remembers? Well, I can factor quite fast, so if I factor and you do the arithmetics fast enough, I say that the results, the roots are -2, -2, and 7, and it's all based by that the -2 -3 times 7 gets -42, which is the last element. And then there is this. Who of you can prove this? Well, for those of you who don't care about IPv6 at all, you can take a paper and try to solve this, and I'm going to continue. Yeah, so how basic is actually IPv4 addressing if you are teaching some networks? And now I'd like to see show of hands actually. Please show me whether it's most basic, whether it's average, or whether it's very complex. Please now, what do you think? Is there anybody who is showing hands? Most basic, it's average, it's like most complex. Yeah, I see some hands, thank you. And what do you think about IPv6 addressing? Yeah, okay, I see some hands being a little bit more on the average side, and some hands being still on the most basic side. Thank you. And now we can move to something more practical. I am quite often doing some work interviews, and because, well, we are doing some networking in the company, but I'm hiring developers mostly. Well, this is my question at a work interview. And I asked that person, please, write an IP address. And they go, well, what IP address? And I say any IP address. Like, remember, find some IP address. Think about something. You are doing some networking stuff, aren't you? And I get this. And I say, do you know what this address is all about? What's behind this address? And they say no. They don't know anything. So I say, well, what about some address you know about? And I get this. Well, I expect most of you know at least a little bit what's this address about? At least the Indian people. So now this is a little bit better. And I ask for a newer address. And they go, oh, maybe this one. And I very much accept this answer because, well, this is actually the address they started getting later in the process. You got those public IP addresses first, and now you are getting these addresses from the private ranges on IPv4 because there is the NAT. We have gotten out of all the addresses. But it's not enough for me. And I ask whether it's actually a really newer one address, which actually is because it was probably allocated after that one before. But they say, okay, let's try a newer one, and they go for this one because their operator first took one private range, and then they found out that it was too little, so they used another private range. And I say, I want a newer version. And now, finally, they know what I want. I want IPv6. And they look at me like this and start writing. and they keep writing, and they keep writing on the paper, and keep writing, and keep writing. And probably here I lose my patience and say, what about this? And they are like, what? This? Ah, I lost the credits from there, sorry. I'll fix that later. And after investigating and asking, I almost always find out that they learn in the school only IPv4. And if they are lucky, they get a little bit of IPv6. But mostly, they get IPv4 only. And always IPv4 first. This is my alma mater. This is the most basic networking course, networking lecture. The first address you see is a local host for IPv6 and is some public address for IPv4. It's an address somewhere in Netherlands, and I don't know what the address does there, but it's there. What's worse, everything else uses some foreign IPv4 addresses, including quad 1, 1, 2, 3, 4, and other stuff. There is no more IPv6 in the whole lecture. In the whole course, there is nothing. So I took another course, which is a whole semester, and the first IPv6 address you see there is this, well, piece of crap. The IPv4 address, I suspect, is the home address of that professor, because it's an address registered to a Czech ISP. What's worse, you get all the thing, all the addressing, you get even an AT explained before you even touch IPv6. You get everything on IPv4 with 44 slides symbolically, and then you get 6 slides explaining to you that it's basically the same with IPv6, but a little bit different. You, as expected, get ARP. Very well explained. You get no neighbor discovery. There's just some protocol very much resembling ARP. Oh, wow. The same I found elsewhere. Oh, does it click? Hey, click. Have I broken it? Yeah, it lights, but it doesn't. Ah, now we are there. Now, if I want to go back, now it works. Yeah, well, if I look at high schools in India, I found some education portal which looked quite official and looked quite well. And you get everything on IPv4, and you get IPv6 presented as proposed. You get a whole lecture material. You get nothing with IPv6. You get everything on IPv4. No comment. I just tried to look at, I was desperate. I tried to find some university that was in the first universities, among those first who were written in those first RFCs, in those 2-cipher, like RFCs with numbers lesser than 100. No, they just hold their IPv4, which was allocated 50 years ago, 40 or something like that. And, well, probably don't need IPv6, I don't know. So, even after looking for everything, I found no single IPv6 first lecture, And I will be still very much happy if you prove me wrong. I was trying a lot. I was asking whoever I could. I found nothing. Well, I was not spam bombing those professors at universities, whether they do actually. And I found, the best what I found was being the IPv4 and IPv6 taught alongside with like a little bit more stress on IPv4. So I asked why. And this was the first and foremost answer I could get. I would expect this answer that IPv4 is everywhere and IPv6 only somewhere from big commercial companies doing all the teaching for money and for the engineers who are trying to requalify into the industry. I am not expecting this from universities. I am expecting them to be a little progressive, at least in an amount that, well, they are teaching this in the first or second year. And the students will stay there for several more years before they actually get into the industry. So they are actually expecting the IPv6 is not going to catch? Are they really sure? I get this answer. They think that the students don't encounter IPv6 in reality, and they are making the reality by this. And this is what I get from an actual network engineer. They tell me that if they are setting up a new box, they always give them the IPv4 management address first, even though the network is actually completely IPv6 capable. It takes additional work for a seasoned network engineer to actually do things the modern way. And I must admit, I have some parts of my personal infrastructure which also runs IPv4 first, because I created it 10 years ago. But that's not the thing. I expect the schools to do different things. So, what's that? Well, IPv4 stays the basic thing, and the schools are reinforcing it. So, how would we like to deploy IPv6 when the IPv4 in schools still rules? Well, we can start with ourselves. For example, documentation. Well, we as developers neglect this a lot. There is like no approach to this, nobody does it systematically, and admit, who of you has read your own documentation, like from top to bottom, in the last 3 years? I must say I haven't. I always update it, I always do a little changes, I sometimes rewrite pieces of it, but I never read it from top to bottom to get some experience, to get recheck how it looks like for a new person. And there are lots of IPv4 examples which are never actually translated for IPv6. You would say it's like obvious that it's also okay for IPv6. But why couldn't do it? Why couldn't we do it in the other way around? Well, why couldn't we have IPv6 first examples and then say, yes, you can also use IPv4. Why not? It's the same thing, but let's admit, if we want IPv6 deployed, we need to have the documentation in a way that it actually shows that the IPv6 is the working variant. And also, sometimes people just don't have enough time to create new diagrams. This is a diagram I created myself just to showcase, because I didn't want to point at any company. But I have seen a lot of these. Like, you take the diagram from a previous presentation, and because you don't have the actual sources, you take the PDF, convert it to JPEG, then you crop it, and then you put it into your presentation. Repeat it 3 times. This is not so blurry as others, but I tried to recreate those JPEG artifacts there, but it didn't work out. And when teaching, well, the theory is almost the same. And if you look into those lectures, it shows exactly this. You get a lot of explanations of the principles, which apply on 4 and 6 the same way. And then there are little differences. What about exchanging the order? We can say, first, let's go IPv6, let's teach everything how it should be. And then we can say, well, in the actual world, you don't get only this. Well, and there is also a comparison for applications. In the real world, with IPv4, you can freely teach that you use SOC Other instead of SOC Other storage. You can teach quirks. I have only one question to the creators of DNS, to the people who actually created Quad A. Why did you have to take 4 bytes? It's 3 more strokes on the keyboard. But again, thanks to the Indian, I think, registry, who runs the open DNS validator on 2409 : which is 1 byte shorter, and this can't be beaten by IPv4. So this is a win for IPv6. Yeah, with routing and forwarding, it's almost the same. Yes, there is the BGP with multi-protocol extension, there is the next generation, there are different things on v6 and v4, but can't we just flip the order? Can't we just say that instead of the protocol being extended to support IPv6, the protocol has been fixed, given a new version, and keeps an IPv4 quirk, which is actually what's there? This is, in the end, a marketing question. This is not a technical one. This is nothing more than marketing, and I know that many network engineers and many teachers hate marketing people, but this is branding. And unless we rebrand IPv6 as the basic, we are not going to move anywhere. Yeah, and I left 2 cliffhangers. This is myself. I am developing BERT. I am occasionally teaching. I am here the first time, and it's nice here, thank you. Yeah, and the second cliffhanger. Yeah, this is thanks, sorry. Thanks for these, because they helped me gathering all the sources. And then the second cliffhanger. Who of you remembers? I have actually included it. So if you are curious, just take a look at the presentation afterwards.
Thank you very much, Maria. We have time for questions. If you do have one, please approach the microphone and introduce yourself. Any questions? Also, just putting it out there, for APNIC training materials, we do try to make it IPv6 first.
John Brewer with a question. In IPv4, there is a block used for documentation.
Sorry, I can't hear you.
In IPv4, there is an IP block used for documentation. There's an RFC that says use this block for documentation. Is there the same for IPv6, and what is it?
If I remember correctly, for documentation, there is 2001 colon DB8, which is like /32, and there is a recent RFC after somebody claimed that 32 is a too short block, that there is, I think, 3FFF colon 20, /20, I don't remember exactly, but there are two RFCs saying that there are two documentation prefixes, and the second one should be very short, should be short enough to allow even for those 29 allocations to be like covered in more scenarios, to have like different prefixes which could be in the real world assigned to different people, different ASNs.
Okay, I'm interested about the problem that you mentioned about how IPv6 should be documented and teach. But as for me, as a student without very much background on it, what document that can you recommend for us if we want to learn or share about the IPv6 first principle in learning? Because as you said, as you mentioned before, it's really there is no good documentation right now, right, for the IPv6 learning.
Well, that's the problem, yes. I have problems finding materials new enough. I have, as you could see with the Indian high school example, most of the examples I could find was actually presenting IPv6 as something being new, being created. So maybe this is even a call for somebody to make some lecture material, because honestly I don't have any. And that's another thing. Please, if somebody knows about this, please share it.
Okay, can I talk to you after this about the teaching this?
Yeah, of course. There is. Catch me after to continue these talks.
Any further questions? Or we can also extend questions for the other two speakers, for John and for Jeff.
Hi, Edmund here. Very good presentation, thank you. I wonder if if you were able to convince any of the schools that you've talked to make any changes. That's one. And actually, personally, I work a lot on internationalized domain names, which is an extension of domains, and we meet a very similar situation about education, and we were actually working on supplementing universities with the education materials that you talk about. So maybe we can share notes on that as well.
I have actually convinced my alma mater to open a course on routing, which has not been there ever. And some people very nearby around me are going to teach it because I can't, for formal reasons, and because I haven't finished the university, actually. But I can criticize. So this course is expected to teach IPv6 first and take most of the examples with IPv6 and do the IPv4 only when needed. And of course, we are going to say that IPv4 is here and it's needed to be done, but when there is IPv6 first, we expect people to do it first, get their hands on it, and not get scared by that strange FE80 something which pops up in their command line and they don't know what it is.
That's super cool. I think documenting that is going to be useful for everyone as well. Thank you.
Yeah, thank you.
If there are no more questions, going once. Okay, thank you very much, Maria.
Thank you.
And that concludes technical session 1. Thank you again to all our speakers and everybody for joining. Please join us again after the tea break for technical session 2. Thank you.
There is only one of you, only one of me. There's a million of those who won't let us be. But they're not gonna see me bleed. 'Cause baby, I got you, 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 you. I've been beaten to the ground, dragged across the dirt. I've been scared to live 'cause some people never learn. But they're not gonna